Now let us look at how recursion uses stack. So I'll take this first example and show you how the stack is utilized. Now already we have seen this model of memory, that the memory is used by dividing into three sections. One is code section, and here I show stack, and this is heap. Now in my program I have two functions, that is fun1 and main. So the machine code of those two functions is already there in code section. Now let us run the program and see how the stack is created. See, the program starts executing from main function. So the first function is main function. In that main function, this is the first statement, that is X is created. So an activation record for main function is created, and it will have its own variable, that is X, having value 3. Then the very next statement is fun1, a call to function 1. So once the function 1 is called, it is having just one variable, that is n. This is the only variable. So activation record for that fun1 is created, and it will have that variable n, and this value X is passed to that one. So it will be 3. So this is for main and this is for fun1. I'm showing you line by line how it is working. Just let us look at it once more. See, the program start executing from main function. The very first thing is X. So activation record for main, and X is created. The value is 3 and the function is called. And that function is having just one variable, that is n. So activation record is created for fun1 with variable n and having value 3. Let us continue. If n is greater than 0, yes, this 3 is greater than 0. Then printf. So as per the tree already we have seen that a 3 is printed. Then the next call, function fun1 is called once again with a reduced value of n, that is decremented value n minus 1. So that function is called again. So once the function is called, we know that activation record will be created, and in that again variable n, and that will have the value 2 this time. This is also activation record for fun1, and this is the second call. Now in that second call, again it checks if n is greater than 0. Yes, 2 is greater than 0. So printf. So 2 is printed. The next line, call again with n minus 1. So right now n is 2. So again a new call, again an activation record is created, and variable n is created with value 1. And this is again a call for fun1. Now again, if n is greater than 0, yes, 1 is greater than 0, print 1, 1 is printed. Then again call fun1, with reduced value, decremented value, n minus 1. So again an activation record for fun1 is created, and it will have the variable n, and that value is 0. This is a call again for fun1. This time, as n is 0, when it calls again, n is greater than 0, so no, n is not greater than 0, it will not enter inside, it will not print anything. Here it doesn't print anything, and it will come out of this conditional statement. So it doesn't enter into conditional statement, so it will come out of the function. And once that call ends, this activation record is deleted. And the control goes back to the previous call. And in that previous call, what it has done, it has called this one. So the next is nothing. So that call will be using this activation record, and that also ends. So again this is also deleted. It goes back to the previous call. In the previous call, this line is over, so there is nothing remaining, and that call uses this activation record, but there is nothing to do. So this is also deleted, and this is also deleted. Then it come back to main. Inside main, after fun1, there is nothing remaining, so this also ends. So all these activation records ends one by one. So this is how stack is created and utilized in recursion. Now, one more thing. What is the size of the stack? Leaving main function, if you count the activation records 1, 2, 3, 4, so only for that function 4 activation records are created. So size of the stack is 4. And how much memory it's consuming? Each activation record is having just one variable, n. So n how many times? 4 times. So you can see the calls here, 1, 2, 3, 4. Already we have done 1, 2, 3, 4. So already we have done tracing. We have generated a tracing tree or recursion tree. So there are 4 calls. So 4 activation records are created. And at the end of this, it will go back and go back. So activation records are deleted again. So size of the memory consumed by this function is 4 into whatever the size of variable integer is. For value of x, that is n, is 3. For value of n is 3, there are 4 calls. So for value of n equal to 5, there will be 6 calls. So for n, there will be n plus 1 calls. So total n plus 1 calls. So how many activation records? N plus 1 activation records. So we can see that the activation records, number of activation records, it depends on the number of calls. So total calls are n plus 1. And what is n? It's a variable. How much memory it's consuming? Now it is integer type. It may be taking 2 bytes or 4 bytes depending on the compiler. So we can say just n plus 1 call. So the total memory consumed by this is order of n. We can mention it as order of n. Why not plus 1 there? See, this is a polynomial, a formula n plus 1, in that degree of the formula is 1. Highest term is n. So we take n. So we write degree there, order of n or degree of n. So we mention the space as order of n. But actually if you see, it is n plus 1 activation records are created. So from this discussion we can understand that recursive functions utilizes stack. So here internally it takes some extra memory for the stack. So there are memory consuming functions. Recursive functions are memory consuming. So that's all I have explained this one. Now already I have a stack, then just I will show you how this function works. So I will use this program as well as a tree. Then also I will show inside the stack what happens. Let us look at it quickly. There are 2 functions, fun2 and main. Both these functions are there inside main memory. Now let us start executing. Program starts from the main function. So the first variable x. So activation record for main is created and having the value 3 in x. And it will call function fun2. Once the function fun2 is called, activation record for 2 is created. So it means all these are for 2 now. So I'll just change them. So the first call, n equal to 3, this is created. That is this one. This is created. Now n is greater than 0. Yes. Then call again. So again it will call with n minus 1. So a new call will create this activation record with n equal to 2. Then again it will call. Then again it will call. See, because the first statement is call. So it's calling itself every time. When n is equals to 0, 0 is not greater than 0. So it will not enter into if block and come out of the function. Once it come out of the function, this activation record is deleted because the function with value of n as 0 has terminated. It goes back to the previous call. In the same function, it will go back to the previous call where it has finished this one. Now it has to perform this. That is this line in the tracing tree. So what is the value of n? It has to print. Now the current topmost activation record is this one where the value of n is 1. So it will print 1. It will print 1 because the value of n is 1 here. And once it has finished, it will come out and this activation record is deleted. It will go back to the previous call. In the previous call, again it has finished the first line, that is this line. Now it has to do this. So print n. So what is the value of n now? So the topmost activation record in the stack, you can see now n value is 2. So this is printed. So 2 is printed. Likewise 3 is printed and all these activation record ends. So you can see that these activation records are created when the function was calling itself again and again. So this is more like ascending. Now once it has reached the last call, that is where n is 0, so it will start returning. So that is a descending. So while descending, it will utilize these values. So all the values of n are there in the stack in the different activation records. So these values are utilized at returning time. So that's all. This is how recursion uses stack. So both of these functions are almost same, only the difference is that this is first printing and then calling, this is first calling then printing. So the activation record created for these functions will be same only. So that's the reason I have taken two similar examples and I have shown you how the stack is utilized. It will be same in both the programs. The size of the stack and the space consumed by this function is also order of n, that is total n plus 1 activation records are created for function fun2, leaving aside main. This is how recursion uses a stack. Now next thing that we have to study is how to find the time complexity of recursive functions. So I will take just one example, this example, and show you how to find the time complexity of recursive function. So let me tell you the basic concept for finding the time complexity. We assume that every statement in a program takes 1 unit of time for execution. Let me give you the idea behind that one. See, suppose there are some books kept here and you have to move the book and keep it in a shelf or in a rack. How much time it takes? Maybe half a second, quarter of a second. Now for somebody who walks very slowly, may take 1 second for keeping one book there, one by one if you have to keep. So time varies from person to person. So we don't mention seconds or milliseconds, we say 1 unit of time. Like if you take the example of currency, $1, 1 rupee, 1 pound. So we say 1. But what is the market value? That may be different. So we say 1 buck or 1 unit of currency. So same way, we assume that every statement takes 1 unit of time. If that statement is repeated multiple times, then you count the frequency, how many times it is executed. So that is sufficient for analyzing our function now. Let us see what our function is doing. It's doing nothing, just printing. So it is printing a value of n. How much time it takes for printing? 1 unit of time. 1 unit of time. How many times printf is written here? Only 1 time. So it is just 1. But this is a recursive function, so it is calling itself again and again. So total how many times it is printing? So let us look at into the tracing tree or recursion tree. Here it is printing 1 time, 2 times, 3 times. So total how many units? 1, 1, 1. So I can say it takes 3 units of time for the value of n as 3. Value of n as 3. So the first value of n is 3. If I make it as 5, then it will take 5 units of time. Then for n, it will take n units of time. So it is just like, coming back to the example, if you have to keep 1 book in the rack, you are taking 1 unit of time. 10 books, 10 unit of time. N books, n unit of time. What is n? Whatever may be. So the time depends on the number of books. So here the time depends on the value that you're passing from here. It may be 3, it may be 5, or it can be anything. So we say the time taken is n units of time. So the time can be represented as order of n. The answer that we got is n units, so the degree of that polynomial is 1. So we write it as order of n. So the time taken is order of n. There is one more method of finding the time complexity using recurrence relation. I will show you how to write recurrence relation and how to solve it to find the time complexity of recursive functions. Now let us find out the time complexity of this recursive function using recurrence relation. We assume that the time taken by this function is t of n. T is for time. If the time taken by that function fun1 is tn, then that total time should be sum of all the times taken by the statements inside. So let us look at the statement. See, there is a statement. This is a conditional statement. How much time it takes for execution? Just 1 unit of time. 1. Then there is a printf statement. How much time it takes? This also takes 1. Then there is one more function call. How much time it takes? 1. As I said, every statement takes 1 unit of time for execution. So this also I have written 1. No, it's wrong. It's wrong. See, that is a function call. So I should know total time taken by that function call. So it is not just a normal statement. It will call again itself. So there is something more behind that one. So I need to know how much time that function call is taking. So let us see closely. When I said this function call total time tn, then this is similar to that one, and this is n minus 1. So yes, this will be taking tn minus 1 time. Yes, this is not a normal statement. There is a function call and it takes tn minus 1 time. Then what is this total tn? I said the sum of all the times taken by the statement. So let's take the sum. So that tn is equals to tn minus 1, the bigger term I am writing first, plus 2. So the total time is tn is equals to tn minus 1 plus 2. So the recurrence relation is tn is equals to tn minus 1 plus 2 when n is greater than 0. When n is greater than 0. What happens when n is equal to 0? When n is equals to 0, it will just check the condition. It will not enter inside and it will come out. So just checking the condition, 1 unit of time. So it takes 1 unit of time. So this is the recurrence relation formed from that function. So the time complexity of recursive function can be represented in the form of a recurrence relation. Now if we solve this using induction method, or also called as successive substitution method, we can get the answer. So let us solve this one. Now before solving this, I should tell you one thing. If you have any constant value here, then let us write it as 1. So that means constant. Now let us solve this. So the recurrence relation is tn is equals to tn minus 1 plus 1. This is the first equation we have. I can solve this if I can know what is the tn minus 1. See, here I write, since tn is equal to tn minus 1 plus 1, then what will be tn minus 1? So if this is n, replace with n minus 1, so this will be tn minus 2 plus 1. So I can substitute this one, tn minus 2 plus 1, in place of tn minus 1. So this I can replace here. So the next equation that I get is tn is equals to 2tn minus 1, tn minus 2 plus 1. So this is tn minus 2 plus 1, and this plus 1 as it is. So this is substituted with this one, and then this plus 1 as it is. So what is this one finally? tn is equals to tn minus 2 plus 2. So let us call this as second equation. Then let us substitute in this place. So what this will be? This will be tn minus 3 plus 1. So if I substitute that, then this will be tn is equals to tn minus 3 plus 1 and plus 2. So this can be written as tn is equals to tn minus 3 plus 3. This is the third equation. So I have substituted 2 times. How long I should do this? Let us continue it for k times. So k times tn minus k plus k. Because this was 3, so this is also 3. If it is 4, then this will be 4. If this is k, then this will also be k. So the fourth equation I got. See, we have to solve this one. So substitute, and then substitute, then substitute, go on substituting until it reduces down to a smaller value, that is n equal to 0, where we know the answer, that is 1. See, when you don't know the answer for a bigger expression, you know the answer for a smaller expression, then break the bigger one into smaller one and solve it. So the same thing we have done. We don't know how much this is, but we know when n is equals to 0, answer is directly 1. So we know that. So we have tried to reduce this and by substituting, and we got this one. Now we say that this n minus k actually has become 0. So on that side I will write down, assume that n minus k is equals to 0. So it means we have n minus 1, that we made it as n minus 2, then n minus 3, and so on, up to what? It became 0. So we assume that this has become 0. So it means, therefore, n is equals to k. So in this equation, if I substitute, that will be Tn is equals to Tn minus n plus n. So at the place of k, I have written n. So n minus n plus n. So I got this one. So this is Tn is equals to T0 plus n. So Tn is equals to 1 plus n. So that's all. I got the answer. Tn is equals to 1 plus n. This can be written as order of n. See, earlier, directly from the tracing tree also I have shown you n plus 1 was number of calls. So yes, I got the number of calls here. And the time taken by this function depends on the number of calls. So yes, it is order of n. So it will be printing for n times and the calls will be n plus 1. That is one more than the number of times of printing. Let us summarize the things that we have learned. See, I have shown you what does it mean by recursion, and I have shown you how to write a recursion. I have traced that one, and I have shown you two different type of recursion. Then I have shown you how a stack utilized, and then we saw how to find the time complexity. From the tree also I have shown you, and by writing a recurrence relation also I have shown you. And the time complexity is mostly written as order of or degree of, that is order of n. See, I'm not using the notations like big O, omega or theta because we have not discussed about them. So I'll give you the idea about these notations at some other time.